Chapter 1, Motion of a Particle in Plane. Kinematics. For introduction, the mechanics are divided into three parts. Kinematics study the motion of the bodies without being interested to the causes of forces. Like we interest to the velocity, to the position, to the time, to the acceleration, like this. For example, moving water in a river. Second, dynamic studies the motion of bodies considering the causes of this motion, forces. The causes of the motion is always the forces. For example, the motion of a box due to the pushing force. And third, static study the bodies in case of equilibrium, for example, equilibrium of a body. A revision from grade 10. Position vector. To determine the position vector of a moving body as a function of time, we must choose a reference frame. The position vector of m at an instant t is r equal om equal xi. The position vector is given by r equal om vector. So it has four characteristics: point of application origin O, line of action the x-axis since is along x-axis, direction from O to M, and magnitude the distance OM. Graphically representation, it's O and it's the point M. So the position vector at point M is from O to M. The position vector. Velocity, it's velocity, not velocity vector. The velocity is the distance traveled by the book over the duration. So V equal d over delta t, where V is the velocity in meter per second, d is the distance traveled in meter, and delta t the time in second. From meter per second to kilometer per hour times 3.6. The units of velocity is meter per second or kilometer per hour. In SI unit, the unit is meter per second. Air quotient table. To study a motion, we use an air quotient table. We record the traces made by the self-supporting book at each constant time interval tau called period of impulse. For example, this is the air quotient table. Here we have a paper, and this is the book. Inside the book we have a needle that make traces. After an interval of time tau, at each tau, the book record traces like this. This is the first traces, and this after tau the second traces, and this after tau the third traces, and etc. So from this point to this point is tau, and from this point to this point is tau, the time. Average speed. The average speed of an object is determined by dividing the distance d the object covers by the duration delta t taken. V average equal d over delta t. If the distance is expressed in meter and the duration in second, The average speed is expressed in meter per second, which is the SI unit of speed. Kilometer per hour is another unit of speed. 1 kilometer per hour, it's equal 1 over 3.6 meter per second, then 1 meter per second equals 3.6 kilometer per hour. For example, the average speed of V14 equal the distance from M1 to M4, so we call M1 M4, over T4 minus T1. T4 minus T1, T4 it's 4 tau and T1 1 tau, and M1 M4 over 3 tau. Or we count the tau, M1 M2 1 tau, M2 M3 2 tau, M3 M4 3 tau, so it's 3 tau. For example, another example, V04, it's the distance from M0 to M4, M0 M4 over 1 2 3 4 tau. Another example, V03 equal M0 M3, the distance between M0 and M3 over, we count the tau, 1 2 3 tau. Another example, for example, V13 equal M1 M3 over 2 tau. Okay. Now, instantaneous speed. The instantaneous speed of a moving object is the speed at an instant t. The speedometer of a car reads its instantaneous speed. The instantaneous speed at an instant t2 is approximately equal to the average speed between two instants t1 and t3 very close to t2, such that t2 between t1 and t3. So for example, v2 it's equal v13. It's between 1 and 3. So v2 equals the average velocity between v1 and 3. So equal m1 m3 over 2 tau. The instantaneous speed it's always over 2 tau. For example, v3 equal v24, so equal m2 m4, since 3 is between 2 and 4, over 2 tau. So it's the instantaneous speed. Average acceleration. The average acceleration vector between t1 and t initial and t final is a average equal v final minus v initial over t final minus t initial. The algebraic value of the average acceleration, a average equal v final minus v initial over t final minus t initial, where v final and v initial are the algebraic value of v final vector and vi vector respectively. The average is the acceleration average is expressed in meter per second square, which is the SI unit of the acceleration. Instantaneous acceleration. The instantaneous acceleration of a moving object is the acceleration at any instant t. At any instant t. So, for example, a2 equal v3 minus v1. The velocity after 2, just after 2, minus the velocity just before 2. So it's v3 minus v1 over t3 minus t1. So a2 obtained equal v3 minus v1 over 2 tau, always over 2 tau. a3 equal v4 minus v2 over 2 tau. a1 equal v2 minus v0 over 2 tau. v1 and v3 are the algebraic values of the velocity at the instants t1 and t3 respectively. t3 minus t1 equal t is the time interval between the instant t1 and t3. Nature of rectilinear motion. If A and V have the same direction at an instant t, A vector and V vector, then the motion is accelerated at this instant, like this. A vector and V vector have the same direction, so the motion is accelerated. If A and V have the opposite direction, like this, A and V has an opposite direction, so in this case the motion is decelerated. As a reference, uniform rectilinear motion. In figure, the distance between m0, m1, m2, m3, m4 are equidistant. While in uniform accelerated rectilinear motion, the distance between the position m0, m1, m2 increases with time. Like m0, m1, the distance between m0, m1 is less than the distance between m1, m2, less than the distance between m2, m3, less than the distance between m3, m4. And in uniform decelerated rectilinear motion, the distance between the position decreases with time. So, the displacement in uniform rectilinear motion is equidistant. In uniform accelerated rectilinear motion is increases. In uniform decelerated rectilinear motion is decreases with time. The velocity in uniform rectilinear motion is constant. The velocity in uniform accelerated rectilinear motion increases with time. The velocity in uniform decelerated rectilinear motion is decreases with time. Acceleration in uniform rectilinear motion is equal to 0. In uniform accelerated rectilinear motion is non-zero positive, it's positive always, and in uniform decelerated rectilinear motion non-zero negative. Time equation for uniform rectilinear motion, the time equation is x equal vt plus x0. The velocity is constant and the acceleration equal to 0. From uniform accelerated rectilinear motion and uniform decelerated rectilinear motion, the time equation, they are x equal half at squared plus v0t plus x0 for both, and v equal at plus v0 for both motion. But in uniform accelerated rectilinear motion, acceleration is constant and positive, while in uniform decelerated rectilinear motion, the acceleration is constant but negative. The graph, displacement graph, for the graph of position for uniform rectilinear motion is a straight line, while in uniform rectilinear acceleration is a parabola, and in decelerated is parabola. In this case, the parabola approach to x-axis, while in this case, the parabola approach to time axis. The velocity in uniform rectilinear motion is constant, so the graph is a horizontal constant line like this. And in uniform accelerated rectilinear motion, the graph of velocity is straight line increasing, while in uniform decelerated rectilinear motion is a straight line decreasing. Acceleration graph in uniform rectilinear motion it's equal to 0, and in uniform accelerated rectilinear motion it's positive and constant, so it's a straight line horizontal, and in uniform decelerated rectilinear motion is negative, so it's a straight line horizontal negative below x-axis. The independent time equation for uniform accelerated rectilinear motion or uniform decelerated rectilinear motion is v square final minus v square initial equal to a x final minus x initial.